Welcome to another online tutorial. Today we're going to be talking about Level 3 Physics Mechanical Systems, Gravitation, specifically through the example of 2015 NCEA question 1 A to D. We do have a few little bits and pieces already on the paper, just so I don't waste too much of your time, or you don't waste too much time watching me write or draw something. Okay, so the question kicks off. Digital television in New Zealand can be accessed by using a satellite dish pointed at a satellite in space. The satellite is used to transmit the signal, and it appears to stay above the equator. Okay, the satellite, with a mass of 300 kilograms, is actually traveling around the Earth in a geostationary orbit at a radius of 4.22 times 10 to the 7 meters from the center of the Earth, and we have put it on there. This is one thing to look out for, because quite often they'll give you the radius of the Earth and then the distance from the Earth's surface to its orbit. And remembering that when you're dealing with gravitation, you're dealing from center of mass, you need to think about what is that distance from the orbit to the center of the mass. Cool. So to start off, we've also got our law of gravitation on the right hand side here. Okay, so Newton's law of gravitation states that there is an attractive force between any two masses, and this is proportional to the product of the masses and inversely proportional to the square of the distance between them. Okay, so we can give it as this equation: Fg, which is our force due to gravity, big G, which is our universal gravitational constant, big M, which is our mass of the larger object, little m, which is our mass of the smaller object, and r squared, which is the radius between the two, and that's from point to point, from center to center. Cool. So question A says, name the force that is keeping the satellite in the circular orbit and state the direction which this force is acting. So we have a satellite moving around or orbiting our planet, our Earth. Okay, what force is acting on it and which way is it acting? Well, as we've just stated, two objects with mass, okay, are going to have gravity acting upon them. We know, okay, because we're avid young scientists, that when you have the force of gravity acting on an object, you're going to have force of gravity and or weight force, however you prefer to call it. Okay, so I always like to use weight. So I'm going to say, and this is not how you would write a normal answer, but I'm going to say F weight, okay, and it is acting towards the center of the Earth. Now obviously when you're writing your own exam answer, you wouldn't do it as this, okay? But I'm not trying to take too much of your time by writing it down. Cool, so we've done the first bit, we've identified it as the weight force, and it's acting towards the center of the Earth. Okay, so B, they actually want to calculate this force acting on the satellite. Alright, so we come in, we're going to say, and we have this equation here. Okay, for B, we're going to say Fg equals big G, big M, little m over r squared. Okay, our gravitational constant, our mass of the larger object, our mass of the smaller object, and our radius from center to center squared. Okay, now this one's particularly simple. It's just plugging and playing information that they've given us in the question. So we come along and we will say 6.67 times 10 to the negative 11. Okay, times the mass of the Earth, which we've been given as well, 5.97 times 10 to the 24 times, and sorry, I'm going to get a little bit mucked up here with my working, 300, the mass of our satellite, and that's going to be over our radius, which we have here, 4.22 times 10 to the 7. Now remember, when you're doing this in a calculator, make sure you use brackets or parentheses, otherwise you can get some syntax error and you'll screw up your answer. Okay, and that comes out as Fg equals 67. Okay, and it's a force, or 67.1, sorry, and it's a force. So when we're calculating a force, we need to give a unit of newtons. Now both of these here are pretty simple questions. We haven't done too much explanation or really dug too deep. So these are both achieved questions. This one here, simply plugging and playing information they've given you in the actual question. This one here, applying a pretty basic theory to the question. Okay, so C gets a little bit harder. Okay, so they want us to show that the speed of the satellite is the speed that they're given, which is 3.07 times 10 to times 10 to the 3 meters a second. Okay, so I'm going to write that down, and just to start off the question, I'm going to write in that velocity. Okay, so we'll say V equals 3.07 times 10 to the 3 meters per second. Okay, now there's actually two ways you can go about this. All right, regarding our satellites, okay, we know that our satellite is accelerating, it is moving around. That velocity as it moves is changing, okay? Therefore it has a centripetal force acting inwards. It is accelerating inwards towards the Earth. As it moves around, its velocity is changing tangent to its path, and hence we get a circular motion, okay? So from that we can infer that Fg, or Fw, our force of weight or our force of gravity, okay? Now we'll say Fg here, the force of gravity, equals our Fc, our force centripetal. Another way you can do it is use our equation from angular motion, that we know that our velocity equals 2 pi r, okay, the distance around, divided by the time taken. So essentially d over t, okay. But our t here is our period, capital T. So 2 pi r, the distance around the orbit, divided by the time taken to complete one orbit, will also give us our velocity. For our sake, I'm going to work through this pathway here. Okay, so we can say Fg equals Fc, and with that we can give the two equations, and we can say Fg, or Fc equals Fg. Doesn't matter which way you do it. Okay, so Fc equals sorry, I got a little bit lost there. Mass times velocity squared over r, which equals our Fg, okay, which equals our equation at the top, big G, big M, little m over r squared. Okay, we can get those out. Those two things equal each other. Right. Relatively chill. Okay, now we can rearrange that equation to make velocity our object of the equation, and we get V equals the square root of gm over r. Okay, now we can plug and play that, and we get V equals the square root of, I'll put in brackets just to make life a bit easier, okay, 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24. Okay, and that's going to be twist the brackets here as if I'm using a calculator, just to keep my working small, so I actually have some space for the next question. Okay, divided by our radius, which for us is going to be the same as before, 4.22 times 10 to the 7. Okay, we do that and we should get the velocity 3,070 meters per second. Okay, now irrelevant of which path you follow, either equating our force due to gravity and our centripetal force together and calculating that way, or saying because we're in geostationary orbit or geosynchronous orbit, we can say, okay, cool, we know that velocity equals 2 pi r over t, and go that way. Okay, personally I think that's a little bit easier, but I wanted to show this working because this is kind of what we're working on. Right, now D is where it gets a little bit harder. Okay, now I'm going to talk a little bit here, so bear with me. But Kepler's law states that any orbiting object, okay, t squared, so our period of orbit squared, is proportional to the radius cubed, where r is the radius of the orbit and t is the time period of the orbit. So NASA uses a robotic spacecraft to map the moon. The Lunar Reconnaissance Orbiter orbits the moon at an average height of 50.0 times 10 to the 3 meters, with a period of 6.78 times 10 to the 3 seconds, And it says the moon has a radius of. So this is just like we talked about before. They've given us the distance from the moon to the orbit and the actual radius of the moon, so we're going to have to add those two together. Okay, so make sure when you do your calculations that you don't use one or the other, that you add these together. And it says use Kepler's law to estimate the mass of the moon, and in our answer they want us to first use relevant formula to derive Kepler's law. Okay, that's most of the legwork, and then once we're there, use Kepler's law to determine the mass of the moon. Oh, so how are we going to do this? Very similar to the previous question, except we're going to take, again, we're going to equate FC to FG, and we're going to kind of use our working from up here. So we're going to say FC equals FG. Okay, and we'll get to the point where we say big M, oh not big M, sorry, MV squared over R equals our big G, big M, little m over R squared. Okay, we're back to this point. Now, we're also going to use the equation V equals 2 pi R over T, because we want to equate period, and in our current equation we don't have periods. We're going to have to bring it in through this velocity. Okay, so this is velocity squared here, so we're going to have to square this velocity. So we're going to have to say velocity squared equals 2 times 2 is 4 pi squared R squared, okay, over T squared. Now our period squared is almost usable. We still need to, oh I don't know what's going on here, we need to make this R cubed and rearrange the equation so we can say that our period squared is proportional to our R cubed. Alright, so stick with me here, we're going to rearrange equations a little bit. Might get a little bit messy, but that's alright. Okay, so now we're going to say, we're going to rearrange everything we've got there, putting them together, making sure that we put in our V squared. So gravitational constant, mass of the larger object, mass of the smaller object over radius squared equals mass velocity squared over R. Okay, so we're just going to quickly, we're going to times both sides by R, get rid of our R on this side and our R squared, divide both sides by smaller mass. That's going to get rid of our two masses, and we're going to get Gm over R equals V squared, and we know that V squared equals this thing over here. Okay, so we can say now that this 4 pi squared R squared over T squared equals Gm over R. Okay, so what are we going to do? Well, we're going to times both sides by R to get this out from under here. So we'll times this by R, times R, we'll cancel out R here, times here. This is going to make this a cube. Now we can kind of see we both have our T squared and our radius cubed. We can form this equation, Kepler's equation, or prove that relationship really quickly. Okay, so if we were to divide by Gm and times by T, we're going to get the equation 4 pi squared, okay, over Gm, okay, and we can put the R squared here, or R cubed here, or we can just chuck it out the side. It's the same, they equal the same thing. R cubed equals T squared. Okay, now we have shown that T squared is proportional to R cubed. So that's the first half of that equation, and it's more than half, it's probably 3/4 in terms of the legwork. We're now going to use this to determine the mass of the moon. So we'll do it quick. We'll go back a little step. We're going to put T back in there and make the mass of our moon, the larger mass, our big M, the object of the equation, and that will give us M equals 4 pi squared R cubed over GT squared, or TG squared, either way you write it. We can plug all the information in there, all the numbers that we've got, and because I'm very limited in space, I won't do that. I don't want to make it take too long, but if you do, you should get 7.38 times 10 to the 22 kilograms as the mass of the moon. So hopefully that has been helpful at discussing an example of gravitation and a few of the ideas that are present. Mainly working through the actual math, because I find this is kind of what holds people up. I would heavily recommend going and doing this example. Okay, if you get stuck using this tutorial as a guide to help you answer it, once you've done that, try one without the tutorial. Give it a shot. If you can do it now and you can do it without any prompt, you should be pretty good. So get out there, get into it, and good luck.